Hello, everyone. It's me, Carolyn, and in this video, we are going to take a look at creating confidence intervals when we don't know the standard deviation of the population, so that sigma is unknown. In the last video, we saw the formulas for the margin of error and things of that nature, and all of them had this sigma in them. However, if we don't know the population mean, how would we know the population standard deviation? So, yeah, what's going to happen is our sample mean isn't going to be distributed normally anymore, but we will be able to still use our same point estimate. We will still use X bar to create this confidence interval. It will still be in the center, and we're still going to have a margin of error going up and going down, but we're not going to be able to use the normal curve anymore. It's not going to be normally distributed. Um, we will look at some other things. So first of all, just kind of remembering us, the standard error will used to be calculated this way with that sigma over the square root of n. However, we don't know sigma. So what we're going to do is we're going to approximate this value. So we're going to approximate it using our sample standard deviation, so S, over that square root of n. And we'll use this as our standard error. However, if that's the case, unfortunately, it's not going to be normal. So we're going to have this margin of error look a little different. We'll have this margin of error equal to a t critical value, and I spelled that wrong. I have an extra L in there, sorry about that. And then S over that square root of n. So we just have a different critical value. We're going to have to find those in a little bit different place. T is a different curve. It is very similar to the normal curve. So just like the normal curve, there's also lots and lots of t distributions. However, the ones that we'll be looking at are all standardized t distributions, so they're going to be centered at 0. But every curve can be standardized to a slightly different t curve using degrees of freedom. So we'll have this degrees of freedom, which is equal to your n minus 1. So in other words, your sample size minus 1. So there's a t distribution with 1 degree of freedom. There's a t distribution with 2 degrees of freedom, all the way down the line. And all of these are standardized kind of values. So they're like multiple standardized t curves. So we will be finding those critical values very similar to the way we do the standard normal, those z stars. However, remembering every single t, every single n value is going to have a different t star. So we're going to have thousands of different t stars. We can't create a simple table of them like we could for the z stars. But our t criticals are going to be very defined the same way. So we're going to find a t that's going to be centered around the 0 so that the area is in the middle. The t curve does look very similar to a normal curve. It does have an area under it equal to 1, but it is a little bit different. So we're going to be finding these t criticals based on, again, using software and so on. So we're going to just jump right in and using SALT again to find ours. And I am going to draw our picture for these guys on how to do that. So we're going to find our T's this time. So we're looking for T star. They are still centered around 0. And we're looking for, again, 90% confidence or 95% confidence. They will be centered around the 0, so evenly on both sides. So we have that 0.95, that 0.90, the 0.85, and then again 0.95. But notice our degrees of freedom is a little bit different. Okay, so to find these, we're going to still go to SALT, but I'm not going to be going to the normal curve this time. So in SALT, okay, we still go to this distribution calculators because we have lots of different distributions. We don't just have a normal distribution, although that one is used quite a bit in statistics. The t distribution, we've already seen the binomial. This t distribution is another one that is probably used very often. The f distribution and the chi distribution are some more distributions that are used over and over again. Unfortunately, we will not see them in this course because we just don't have the time to get to them in this class. So we're going to be using the t distribution. Now notice the t distributions are all the same. They're all centered at 0, so we don't have to enter means or standard deviations. All we have to do is enter our degrees of freedom. And remembering that the degrees of freedom is n, your sample size, minus 1. We will be using the same sort of buttons. Notice the curve looks very similar. And we will be using our between as well. So the first one had a degrees of freedom of 6. So I will put that 6 in my degrees of freedom. And we were looking for the 95% confidence interval or 95% confidence level. So that's our 0.95. And we'll get that our T star is at 2.4469. Changing it to the next one, we had a degrees of freedom of 17 and a 90% confidence level. So our T star was 1.7396. The next one is our degrees of freedom is 26, which would mean our sample size is 27. We are doing a 85%, so 0.85, and we get 1.4834, 1.4834. Notice when we're doing this too that the curve shifts a little bit to being steeper and more flat based on those degrees of freedom. They do a much better job of giving you a more accurate picture in this software as well. Now our last one is a 75 confidence level, and we're doing a 95, and this is 1.9921. Okay, so we're going to be doing some of the same sorts of things that we did in the last video, but this time we're going to be looking at them from the T situation and trying to figure out how to use it in order to get our pieces. So I'm going to go back to our video, or back to our notes, I should say, and we'll do some more examples. Okay, first of all, just kind of recap our T stars, how we got them. We went to SALT, we went to the T distribution, making sure to put in our degrees of freedom and using the between. So this would have been a negative 2.4469. This is a 2.4469 there. T stars on both sides, 90% in the middle, making sure to change the degrees of freedom each time. Okay, let's do an example where we're just going to find that point estimate and we're going to find that margin of error. So remembering our point estimate is X bar and the margin of error, that has not changed, the point estimate hasn't. But our margin of error this time is our T star times our S over that square root of N. So in this case, our point estimate will be that 29.4. So there's our point estimate right there. Point estimate. And our margin of error, well, we'll have to find our T star for this particular situation, but our S is 3 and our sample size is 12. So since our sample size was 12, our degrees of freedom, which is n minus 1, will be 12 minus 1, or 11. So we're going to go back to salt to find that T star. So going to salt. Okay, we would have 11 degrees of freedom. You'll notice how flat, a little bit flatter it got. And we wanted a 95%. So our T star is that 2.201. Okay, and we'll go back one last time to our notes. Not one last time, we go back and forth throughout the video. Okay. So there's my 2.201 that I got from salt. I'm going to take that 3 and divide it by 12. 3 divided by the square root of 12, sorry. Square root 12. Then I'm going to multiply that by 2.201. And I come up with 1.906121914, however many digits we want. So now we have a way to get an interval based on this situation. Our center will still be at that 29.4, and we're going to go up and down the 1.906 to get our confidence interval. And that's what we're going to be doing next in a moment. But first, we'll do one more example here. Just kind of picking all the pieces. Okay, so and we'll actually put this one all the way through. So we have the term freshman 15 is often used to describe weight gain in college students their first year. So what they want to know is really how much do freshmen really gain? So they took a study of 125 students, and they found that the average weight gain was 2.7 pounds, and that the standard deviation of that sample, so they went and actually calculated, they got all 125 people, put it in probably a spreadsheet of some sort, cranked out the mean, cranked out their standard deviation. So this 2.7 in terms of symbols is your X bar. This 6.4 in terms of symbols is your S. This is your sample mean and your sample standard deviation. Being able to know what symbols each piece represents is pretty important. Oh, it looks like I have another typo. That's the O. Yes, please overlook my typos. All right, now we are going to be calculating our 90% confidence. So we want to find the estimate for the true mean and then our margin of error. So our estimate, that's what we're using. And that's actually the estimate for mu. And the estimate is this X bar. So that's going to be our 2.7. Our margin of error, that's M. Since we do not know our population standard deviation, we will be using a T star for this. And then that's S divided by that square root of N. We'll be going to salt in a moment to find this T star. But S is 6.4. And our N is 125. That's our sample size. Note that our sample size affects our degrees of freedom, which we will need in salt. So our sample size minus 1 is our degrees of freedom if I'm doing this by hand. So we're going to go back to salt and get our T star. Okay, so our degrees of freedom was 125 minus 1, so 124, very, very skinny. And we are looking for a 90%, so change that to a 9. And our T star is 1.6572. 1.6572. Okay, which I put into our formula. Oops, why did we not go back? There we go. click the right buttons. There we go. Into our formula for that T star, we're going to take my 6.4, divide that by the square root of 125. Take that value times my 1.6572. And I get 0.948636634. Not sure how many decimals we want to use. I'll just put them all that I got from my calculator on here. So now again, that's our estimate, which is going to be the center of our intervals. And then we're going to go up a little bit and down a little bit, up and down a little bit, that margin of error to create the interval that I am confident my true value is sitting somewhere in. So if you wanted the formula for this, if our standard deviation of the population is not known, so this means that sigma is unknown, we have to approximate it using S. That's our sample standard deviation. And notice that when we have our sample standard deviation, we don't have a Z critical value. We don't have a Z star. We have a T star, so a different curve. We're going to find that 90% confidence level for this weight gain problem that we did above. We already did all of the work in the previous part. I'm just going to write our formula down and put all our pieces in. So the X bar that we had before was our 2.7. We would add and subtract the T star, which we got from SALT. My S was the 6.4, square root of 125. This turned out to be, when I calculated it, 0.94, I'm just going to go 4 decimals, 86, to which I will add and subtract 2.7. I will take 2.7 and add this number. That's going to give me 3.6486. And I will also take 2.7 and subtract that. That gives me 1.7514. So there is my upper bound and my lower bound of this interval. I like to write it in interval notation. Sometimes people would just want to know the upper bound and the lower bound, and you can list them that way. So this was 1.7514, 3.6486. But what this means is I am 90% confident that the true weight loss or weight gain, weight gain of new freshmen is somewhere between 1.75 pounds and 3.65 pounds. So a lot less than the 15 they were talking about for this situation. Now, it is possible that we took a bad sample. So that's why it is very important when we're doing things like this to make sure that the sample we take is unbiased. We don't have any biases showing up, and they're randomly selected so we can get a nice broad overview of all of our freshmen. Maybe they took 125 college athletes. And in that case, athletes aren't going to be gaining as much weight as some of these other students who may gain quite a bit more weight. So you have to be a little bit careful on how we get our samples if we want to make these predictions about what the true weight gain is. So be aware of that. Okay, let's do another one. And I think this time we're just going to answer the question before we do another example. Let's say we did a 95% confidence level for the same thing. So what's going to change? Well, let's see. Would the X bar change? Let's put our formula down here. Plus or minus T star S over the square root of N. And we will actually calculate this and find out. So my X bar, well, that's not going to change. That's still 2.7. We will add and subtract. T star does change because we're changing it to a 95%. So we're going to have to calculate a different T star. My S has not changed. and my 125 has not changed. So we're going to go and get my new T star. Now, thinking about what we're doing, we're going from 90% confident to 95%. So gathering 90% of our data to 95, we got to make it bigger. So we should see this get larger. But I just want to do this one to illustrate that, yes, it does get larger. So we're going to go to salt and get that T star for the 95%. I should still have everything typed in for this example. So it was 124 was our degrees of freedom, the n minus 1. And we're changing from 90 to 95. You'll notice our thing does get wider. Not a lot wider, but a little bit wider. So we got 1.9793. Okay, I've got that value. Put it into my formula. I wrote it down. So I'm going to multiply all that out. So that 1.939793 times that 6.4 divided by the square root of 125. And we're going to be adding and subtracting 1.133. And I'm just going to take 3 decimals because the next one's a 0. So that's going to bring it up. If I add these, I get 3.833. And if I subtract it from the 2.7, I get 1.567. So there's my new lower bound and my new upper bound. Comparing those to what we had before. This is what I had before. Notice it does go down a little further and up a little bit more. So it does get wider. So here it was before, it does get wider, both down a little bit more and up a little bit more. So increasing my confidence level causes my intervals to get larger. If I'd increased my sample size, my answers would get smaller. Okay, let's do another example. A survey wanted to know how long people spend in the shower. So we randomly surveyed 100 random people and said, how long do you shower? So they said that the mean amount spent in the shower is 8 minutes, and we have a standard deviation of 5.14. We want to find a 90% confidence interval for the true mean amount spent in the shower. Okay, I'm going to do this one a little bit differently using another part of salt just to introduce you to another piece of salt that can actually do these even faster than what we've done before. So before we did the formulas, we cannot use the distribution calculator because if you remember for a t, they are all centered around 0 because those are all our standardized t-scores. So there's no way to change the mean of those or the standard deviation. So we have to use something a little different. Okay, I am going to kind of write some of these pieces down just so that I have them all. So we have our n, that 100 is my sample size. So n is my 100. If I need degrees of freedom, that would be 100 minus 1, which is 99. Just so I have all my pieces ready to go. This 8 is my X bar, so that's my sample mean. And my sample standard deviation, so my S, is that 5.14, and that's my sample standard deviation. I'm going to abbreviate a little bit. And I want to find a 90% confidence level. So 90% confidence interval. I'm going to abbreviate confidence interval here. So I'm going to go to salt. And we're actually going to use, like I said, a different part of salt to find this. And like I had mentioned when we first started talking about setting up confidence intervals, we're doing our first little taste of inferential statistics. So that's why we're going to be going into this inferential statistics area. Okay, we are going to be using this one sample T. Notice it is a T. It's not a Z. It's our T. And we have a couple of options. So we have our sample mean, sample standard deviation, and sample size. Those three pieces are the information we want. So our sample mean, writing that down, that was an 8. Our sample standard deviation, that was that 5.14 pounds that we had. I guess it wasn't pounds, it was minutes. And our sample size, notice they asked for sample size, not the degrees of freedom. Our sample size, which is our N, is 100. And now that we have two options, we got a couple of buttons we could choose. We could choose the hypothesis test, which will be later in this course, or confidence intervals for our mean, which is exactly what we are calculating. So we're going to click that button. Notice they ask for the confidence interval size. We want, for this problem, a 90%. So I'm going to get all of that information in right there. And then we want to generate the results. There we go. Some things I kind of check is making sure that the pieces I typed everything in right. I can easily go back and change. So there's my sample size right there, my mean, my standard deviation, the standard error, that's the S over the square root of N. So if I took 5.14 divided by the square root of 100, that gives me this. There's the degrees of freedom. Here's my lower bound and my upper bound. My lower limit, so I'm going to write it in that form, 7.146559, and we're going to go up to 8.853441. All right. So again, we went to inferential statistics using SALT, which is a Cengage learning product. We're using the one sample T because this is finding a using the T curve for basically one sample. We only took one sample. We have a sample mean of 8, our standard deviation, our sample size. We clicked confidence intervals for our mean, and then we put in the confidence level we wanted, and we hit the green button and did generate results. We could reset it and start all over if we wanted to. But we'll go back to our notes to get one more example. I think one. I got two, but not going to do the next one for reasons we'll see. All right, so now we're going to do, let's say we want to find a 95% confidence interval for the average on a statistics exam if the mean of 15 students was 87% and the standard deviation was 2.4. So my N is 15, that's the sample size, how many students took the test. X bar, the mean, is 87%. And my standard deviation is 2.4. Okay, and we are doing a 95% confidence level. So 95% confidence interval. So I'm going to go to SALT and let it do all the work for me. Okay. So in SALT, if I were just coming in, I want to make sure to go to inferential statistics, which default is the one sample T. We are going to put in my sample mean, which was an 87, that was the average. My standard deviation, which was 2.4. And the number of students, the sample size is 15. Notice we don't have to worry about things being bigger than 30 like we do with a X bar or knowing the standard deviation. We can just jump right in. I do want my confidence interval for mu, but we're doing a 95%. Nothing's changing and nothing will change until I actually click that generate results. And then it was very fast. You may not even have noticed, but it did change from the N before was 100. Now it's 15. My mean is 87. You can double check making sure you typed everything in correctly. Standard error would have been that 2.4 divided by the square root of 15. So that's what's being added and subtracted. And we're lower limit, 85.67. And our upper limit, I'm just going to abbreviate, 88.33. Yes, you could put all the digits in depending on what whoever you're doing this for asks for. So choose whatever amount of digits you need. I mean, if you're doing it for homework, pick the number of digits they want. If you're doing it for a report of some sort, choose whatever feels more comfortable. Okay, so I just did 2 decimals, mostly because there was a nice 0 or something in there. So 85.67 was my lower limit, 88.33 was my upper limit. And when they did generate the results, I did double check my N, my mean, and my standard deviation. Okay, another example that I'm going to do here is one that we've seen before, parents looking for when their kids walk. Again, I'm not actually going to go through this one because I cannot simply type all my data into SALT, but we could. We could type all of this data into a spreadsheet if we wanted to, calculate the mean, calculate the standard deviation, and then dump that information into SALT as well. If I'm doing it as a homework problem, I hit the SALT button and all the information goes right into SALT for me. So I don't have to do a whole lot. It kind of you just have to know exactly where to go to get what you need. So playing with SALT when it's hooked up to the homework system is really, really slick. When it's not hooked up to your homework system, we will have to use software or do it by hand. Not that I recommend that. I would type all of this into a software situation like into Excel or into Google Sheets and calculate the mean and the standard deviation that way. And then finding my confidence interval using SALT or doing it by hand because the formula is not all that bad. Okay. The next thing I want to look at is how do we find that N? Remembering we were saying we're starting from scratch and we want to find how many people do we go out and survey or how many things do I measure to get a interval that is 99% accurate within 2 meters or whatever the margin of error is that I want. Okay, so I'm going to start with our formula. So again, our formula for the margin of error looks like this. Solving it looks something like this, which I could rewrite as T star times my S all over my M and then square it. Okay, we have some problems and you might not notice them right off the top because, you know, we are looking for N. Well, if we are looking for N and we needed to calculate T star, the thing we need for T star is degrees of freedom. And degrees of freedom is N minus 1, but I don't know N. So I can't do degrees of freedom, so I can't find T star. Also, if I haven't done anything, I don't have a sample. And if I don't have a sample, I don't have an S. So we have 2 problems. There's my 2 problems. Okay, we don't know those 2 things. We don't know T star and we don't know S. How can we find them? So what we do, okay, what we do is we will use our Z star to find instead of the T star. Okay, and we're going to use a really rough estimate for S. And the rough estimate we're going to be using for S is the following. And this will be pretty good, roughly speaking. It's a lot of times a little bit of an overestimate than an underestimate. We're going to just take the range. So we're going to, sometimes we might even have to estimate our range. You know, maybe we're talking about weight gain that we were talking before. And our weight gain, we know, well, some people aren't going to gain anything. Okay, if we're talking weight gain, we could even talk about negatives, you know, because range is just how distant we are. So maybe we're thinking, well, people could lose anywhere from 15 and gain anywhere to 50 pounds. Just being overthinking. So that means our range would be 65. So doing that subtraction. And then we divide it by 4, basically to get the quartile kind of idea. The way this is read with this little, I don't know, it's like a little caret over the top. We read this as S hat. So that little caret that's on the top is read as a hat. So we will see hats on other letters as well. So S hat is an estimate for S. And we use that, is going to be our range divided by 4. So it's an estimate that we use for S when we don't have it to find our N. So here, let's do some examples. But first of all, rewrite our formula. So our formula now is going to be our Z critical. We'll have that S hat in there divided by M. So let's say, I'm going to just write it a little bit different, Z star, S hat over M, all of that squared. Okay, so what's going to happen to our sample size if we wanted a smaller error? Well, our sample size, if this is going to get smaller, our sample size has to get bigger. So we want a smaller M, we need to ask more people. What's going to happen to our sample size if our standard deviation is really, really large? If this is really, really big, our sample size will also be very, very big. So these will affect the sample size. I also want to remind us that we always round up. For N, because it has to be a whole number. Because we don't ask 5.3 people, we will ask 6 people. We aren't going to measure 16.42 cans, we'll measure 17 cans. We always round up, because if we don't, we're not going to quite get the margin of error that we want or that confidence that we want. Okay, so here's some examples, and I do have 2 of them. So first of all is about books. So a college financial advisor wants to estimate how much students are going to spend on textbooks per quarter or semester. For this estimate to be useful, we want to make sure the margin of error is somewhere between $20. So making sure that you have within $20 high or low, that we're accurate. He also thinks that, we spend a lot of variety on textbooks, and you could make this larger if you wanted to, but he figures most students will spend anywhere between 150 to 550. So the bottom end would be 150 up to $550. Now, this would also vary from college to college. Some places you might even want to say the bottom end would be 0, because maybe you have professors that use a lot of online materials and they don't require you to spend any money for textbooks. Other programs or degrees have larger amounts, like the law degrees, you have lots of law textbooks, and those tend to be very, very pricey. So maybe you have an upper end, or if you go to Yale or someplace more prestigious, your textbooks are more expensive. I don't know. But for this college, they're saying somewhere between $150 and $550. So we want to find a sample of students and find out how much they spend on their textbooks. And we want to be within 95% confidence. So he's got all his things kind of set up. He's going to find his N. So our formula for our N, since we don't have any information whatsoever, we're going to use a Z star, an S hat, all over M, and we're going to square it. Now we have to drag out our table again for those Z stars, and the Z star for a 195% is 1.96. So I went back to my table, or I went to SALT under the standard normal and got that Z star. S hat is my range. So range again is your largest value minus your smallest value. And we're going to divide that by 4. So that gives me 400 divided by 4, which is 100. So we multiply this by 100. And my margin of error is the amount we want to be within. So we want to be within $20. And that we're going to square. So this is where we drag out the calculator. We take 1.96 times my 100, divide that by 20, and then I'm going to square that number. I come up with 96.04. Now remembering n is a whole number, and we want to always, always round up. The n we will use is 97. So I want to make sure to go and get 97 students and ask them how much they spent on their books this semester or this quarter, whatever you're looking at. And we can use it to set up our confidence interval. And at that point, we can also go back to our T, because now we have a sample, we can calculate the standard deviation. So we can use the T in the correct pieces. We'll probably get a much better situation, but we can find our 95% confidence level for this using the right methods. Here we are kind of just estimating a little bit. And I might even, if I were doing this, to be honest, I'd probably choose 100 people just to be on the safe side, because getting more people, I'm going to be more accurate. All right, so here is another example. So we have this tennis association. A tennis ball is supposed to bounce somewhere between 53 and 58 inches from the ground on concrete. When it's dropped from 100 inches above on the concrete, that is 4 inches thick. Wow, lots of details. So we've got 4-inch concrete, dropping a ball from 100 inches. It's supposed to bounce back 53 to 58. An inspector needs to verify that these balls produced from a certain machine will meet these standards. So he wants to figure out how many does he actually have to do this to. So he's going to be dropping them from the 100 inches and measuring how far they drop up. If this is for, some of these major competitions, we want to make sure the balls are accurate. So he's going to be doing this, but he doesn't want to do it too often because it sounds like a lot of work. Measuring 100 inches, dropping it, measuring how far they bounce, that's a lot of work. Okay, but he wants to be 99% confidence, and he wants to make sure he's within an inch. So he's going to be, an inch, not very far. So how many balls does he need to look at? So again, we don't have any information about S or sigma, so we use that S hat. So it would be my Z star, my S hat over my M, and we are going to square it. My Z star for my 99 is one that I don't have memorized. So where's my table? I'm finding my table. There it is. 2.576. My S hat I have to calculate. So S hat is the range divided by 4. Now the range of where these are supposed to is 58 to 53 inches divided by 4. So that's 5 over 4, which is 1.25. And we have to be within an inch. So that's how our margin of error. And we're going to square this. So now I drag out my calculator. 2.576 times 1.25 divided by 1. And we're going to square that. And we get 10.36. So we're going to take 11 tennis balls and bounce them. Thank goodness, that shouldn't take us too long. So he's going to bounce 11 tennis balls and make sure that they are within that 53 to 58 range and actually calculate them. And then we'll see if they're good enough for this event. If not, they'll find different ones from a different machine that's a little bit better. Okay, but this kind of ends the sample, well, the confidence intervals for mu. We're going to look at a different confidence interval in our next video when we're going to turn and look at something a little bit different. We're going to be looking at sample proportions, but we'll look at that in the next video. So I hope to see all of you then. If not, have a great day anyways, but I'll hopefully see you in the next video. Bye.